In the previous video, you were told that we would finish this video in class. That's what I'm going to do now, but I'm actually going to go back all the way to the beginning of the problem that he was working at the end of his video. So we'll be going back through it, just consider it a review. I'll be adding some issues that I found along the way as well. So we're on kinematics part 3 for principles of engineering, and we have a projectile motion problem where a ball is fired from a device at a rate of 160 feet per second with an angle of 53 degrees to the ground, and it lands after 8 seconds. So just a few pieces of information we have here. We have an initial speed. I'm going to label that VI equals 160 feet per second. We have an angle that it's fired at, so we'll call that theta, is 53 degrees relative to the ground, and it lands after a time interval of 8.0 seconds. So as we look at this from the standpoint of a diagram of the scenario, we have a projectile fired from this point. It follows a parabolic trajectory, which is the pathway of the projectile, of this device, or of this ball, excuse me. It reaches a maximum height about halfway through its trajectory, fired at 53 degrees. Now, since it's fired at an angle, we draw like this, we have the velocity along the actual trajectory at the beginning of being VI. That was our 160 feet per second. But like any trajectory, or in any vector that takes on an angle, is going to have components. So we have an x component and we have a y component to our original speed or velocity. So we would call this VI in the x, and we would call this VI in the y. And you can think back to some of the things that we did with our truss problems, where we were solving for components of individual forces along moments, or along, members in a truss. And so we have our trajectory like so. Okay, we want to find in the end what the range is. R here stands for range, and this would be represented by x max, because it's the horizontal motion of the actual projectile. All right, so let's start by finding the x and y components, and we also want to know what's the ball's range. We're going to find what is the ball's range by first finding the x and y components. So to find the x and y components, we will look at our triangle that we had drawn. This is a little bit messy, I guess you could say, in that it's it has the trajectory drawn in. But if we were to sketch this out, we would have our x and y axis. We've got our VI here, and we've got our VX along the x-axis here, and our VY along the axis here. And this back here is nothing. I'm not sure why that showed up. Alright, so back to our pen. So this is VI in the y dimension, VI in the x dimension, and they add by the Pythagorean theorem to give the sum, or resultant vector, which is what we're calling VI. So we can see that VIX is this is our 53 degree angle here. VIX is adjacent to our 53 degree angle. So we would say that since it's adjacent, cosine of 53 degrees is equal to the component VIX, the adjacent side of the triangle to the 53 degree, divided by the hypotenuse, which is VI. And just with a simple cross multiplication, VIX, which is here, is equal to VI times the cosine of 53 degrees, or cosine of theta, which happens to be 53 degrees. So plugging that in, let me erase all this ink. Plugging that in, we get the cosine of 53 degrees times VI. So this is the cosine of theta. This is VI, 160 feet per second. Throw that in your calculator and you're going to end up with 96 feet per second. And then we want to know the ball's range. Now you'll notice that we didn't really find VIY. And the reason for that is because the range is dependent upon the x velocity and upon the time of flight. And the VIX velocity is constant. So horizontally, there is no force acting on the ball in the x direction. There's only gravity acting upon it. So if we have constant velocity, that means we have, if we have constant force, that means, or zero force, I should say. If we have zero net force, that means we've got constant velocity. And the equation for that is just simply velocity, here we're talking about the x, is equal to the distance, or the range, which is x, divided by the time that it takes to go through that range, so divided by t. So we're going to have Vx times t equals range. Okay, so following through on this, here's your Vx. We found Vx to be 96 feet per second from the previous slide, and the ball lands after 8 seconds. So x max, or the range, is just simply equal to 96 times 8, and that comes to 768 feet. Now, we can do the same thing. Here we've got a golf ball that's hit at an angle of 20 degrees to the ground. So we have a golf ball that's going off from the ground at an angle of 20 degrees. And it has an initial velocity given along the trajectory of 100 feet per second. And it lands, time equals 3 seconds. And we want to know how far it goes. So we're going to find the horizontal distance by saying the horizontal distance, x, equals VIX times t. And VIX, if we look at our triangle again, this is VI, this is VIX, this is 20 degrees, then the cosine VI times the cosine of 20 degrees equals VIX. So we can substitute that in right here and say that x max, or the range, equals VI times the cosine of 20 degrees, which is just VIX, times time. So let's do that. We had VI was what was that, 200 or 100? 100 feet per second. So 100 feet per second. So we have 100 feet per second times the cosine of 20 times a time of, I believe it was 3 seconds. 3 seconds. And that comes to a total of 281.9, so let's just say 282 feet with seconds canceling, leaving feet. Cosine 20 has no units. It's 282 feet. Let's take a little bit closer look at the theory behind all this and why we're able to do some of the things that we do. This was mentioned in the video, but I'm not sure how clear it was, and I'm hoping I can clear it up some. Maybe I'll make it muddier. We'll see. Let's say that we have a projectile and we can define a projectile as an object that's moving through the air that is only subject to the force of gravity. There's no other force acting on it. That is, if we can assume that the object leaves the launcher and there's no more force applied, so the launcher and the object that has been launched as a projectile are no longer in contact, and we can also assume that air resistance is negligible, although we know that some things would have some pretty significant air resistance. We're going to consider things that are sphere-shaped, like a steel ball bearing, or something that's shaped like a bullet or a rocket, or something that would have good aerodynamics and low air resistance. It also will be in the air for a very short period of time, so there's not a lot of time for the air resistance to have a tremendous effect. So what if we could fire a projectile, but there was no gravity? Okay, so we have no gravity whatsoever. What would it look like? And I'm speaking of graphically, what would it look like? And we're going to look at what it would look like if we drop an object, and if we had a horizontal launch and then a vertical launch. So horizontal means that we would fire it, parallel to level ground. Vertical launch, we would fire it up at 90 degrees. Drop in an object, it would fall at 90 degrees to the surface of the Earth. So we have a steel ball that's dropped from, we're going to drop first. A steel ball is dropped from a position that's 25 feet above the ground. What is its position at each 0.1 second interval until it hits the ground? Well, the first thing you're going to want to do is consider a free body diagram. Okay, so we sketch the ball. It's dropped. It's going to, at this position, we'll call this 25, and it's going to fall to, or it's actually, this would be the 0 position, and there is no gravity. So what's it going to do? Okay. Well, if we drop it and there's no gravity, then the ball's not going to fall. Okay, it just remains in place. So you can see that the graph itself, if I'm at 25 feet and I drop this ball in 0 gravity, I don't throw it, I don't give it a push, I just let go of it at 25 feet through this time interval that we're looking at here. It's going to just remain in place. This is about 1.5 seconds, I think. So it's just going to remain where it is. So its position is constant. It has 0 net force. Since there's no gravity, we've turned off gravity. Therefore, we have constant velocity motion. And we would actually say here that we are at a force equilibrium. There's nothing to change its state of motion. If it was at rest to begin with, when we let go of it, it's going to remain at rest because there was no force applied to it. All right. How we're going to throw it horizontally. Okay, so we have a steel ball that's thrown horizontally with a velocity of 1 foot per second from a position that's 25 feet above the ground. What's its position at each 0.1 second interval until it hits the ground? Okay, so, and we're saying until it hits the ground, that we don't even know that it's going to do that necessarily. So don't let that throw you here. So a steel ball thrown horizontally with a velocity of 1 foot per second from a position that's 25 feet above the ground. So imagine that you've got like some sort of cliff or something. There's the ground down there. Person throws the ball up here, and it goes perfectly horizontally with the ground below. And from here to here, we have 25 feet. So what's that going to look like? Well, what we're going to have, and this appears the way I've got this graphed. Notice that we're looking at the x position here, so where it is along the x-axis, and this would be a logical place to call 0 here. And it looks like maybe the hand let go of it at 1 foot from the edge of the cliff, and then it just keeps going. Okay? If you look at this, this is very linear. Okay, and because it's linear, we can say that is actually the velocity is the slope of this graph of position versus time. Okay, and since our slope is constant, then that must mean our velocity is constant. So if we've got a constant velocity scenario, that means that our force is constant. So the ball leaves the hand at 1 meter away from the edge of the cliff. So here's the edge of the cliff, not 1 meter, but 1 foot. So from here to here is 1 foot. And ball leaves the hand, there's no more force from the hand. There's no gravity in this strange place. So the end result is that once the ball leaves the hand, there is a net force equal to 0, which means constant velocity motion. Okay. So let's go in a different dimension. Let's take a steel ball and throw it straight up with a velocity of 1 foot per second from a position that's 25 feet above the ground. What's its position at each 0.1 or 1/10 of a second? All right, so thinking about this again, when the ball leaves the hand, it's no longer in contact with that, so there's no surface force or contact force that is the result of the hand pushing the ball. And there's no gravity, so once it enters the air, not in contact with anything, F net equals 0. So if F net equals 0, we should predict a constant velocity. Alright, so if it's got constant velocity, that means if we graph position versus time, we're going to have a linear plot. And that's what we get. So we're throwing it from the 25-foot position, and we're watching this ball go straight up. Now, don't let the slope of the graph confuse you in terms of what's happening to the actual ball. If we've got our cliff here, and our ground down here, and the ball starts at this location, then every second it's going to travel a little bit further up, but if I can get my points to stay, the distance between these points recorded every second, let's say, is going to be equal. So this distance per time equals a constant. So if we're graphing this from the standpoint of not just the position, seeing where the positions are located, but looking at the position versus the time, we get a linear constant velocity plot, and the slope equals the velocity. Okay. So how do things change if we add gravity? If we add a force. Okay. So first, draw the free body of the object while it's in the air, and consider the forces to determine the motion that will result. But you have to remember that these go back to Newton's laws. If the sum of the forces equals 0, then we're going to get constant velocity motion. But if the sum of the forces is not equal to 0, that results in an acceleration of the object in the direction of the net force. So whichever direction the leftover force is, That's the direction that the object is going to accelerate. That does not mean that's the direction it's going to move, only that it's the direction it's going to accelerate. So let's say that we have an object, steel ball again, it's dropped from 25 feet. We now have gravity, so it's going to fall to the ground. Okay, so we want to sketch the ball. So let's say that this is at 25 feet. And down here is 0 feet. Okay. So the ball is going to fall, and it's going to accelerate as it goes through that 25-foot fall. Okay, so here's the graph of what it would look like. This is a graph of what it would look like. And keep in mind, this is the y position versus the x position. So this is not versus time this time. So the object is going to fall straight down. It's not moving horizontally. It's only moving vertically. And as it falls, look what's happening to the separation of the positions. Each of these is a position at a tenth of a second. So 1/10 of a second, 2/10, 3/10, 4/10, 5/10, 6/10 of a second. The spacing or the displacement is becoming greater. So each time interval that passes between each of these dots is going to be the same, so is increasing with constant time interval. Okay, so that's what it means to accelerate. In this case, we've got an acceleration that's going to cause the object to speed up. Okay, that's not the only way accelerations can work. We would also say that since acceleration and velocity is a vector, here we've got a velocity that's in the, this is our start point up here, and this is actually our end point right here, because the 0 would be the ground level. So it never actually makes it to this last point down here, unless there's a hole. But as it's falling, it's speeding up. Its velocity is downward. That's a negative. And its acceleration is also pointed downward, which is negative. So here we have a negative and a negative on these two quantities. Velocity and acceleration have the same sign, therefore it's speeding up. Negative acceleration does not mean slowing down. It depends upon what the velocity is. So to explain that, if you drop the projectile from a high position, then we've got a net force that's not equal to 0. So we've got F net is equal to m times a. This is Newton's second law. And for an object that's falling near Earth, it has a constant acceleration that we call g, the acceleration due to gravity. That value is either, depending on the unit system you're using, it's either 9.8 meters per second or per second squared, or 32 feet per second if we're looking at the imperial system. So Newton's second law becomes F net equals mg, where g is the acceleration that's caused by gravity. And gravity here is the net force. So if we draw that free body diagram at any position, if this is the ball and we draw a vector for the force, the vector is going to be straight down, and that would be a force due to gravity, which is equal to m times g, which is really just the weight of the object. So the equation describing the position as a function of time, however, is not F equals ma. This is force, mass, and acceleration. We want to know what's the position, y, as a function of time, t. And that equation is this. We have the position at time t is equal to 1/2 the acceleration due to gravity multiplied by the square of time, plus the initial velocity that it has in the y dimension times time plus its initial position. Okay, so again, these values, this is position at a time. This is 1/2 acceleration due to gravity multiplied by the time that we're looking at squared, plus VIT. VI is the initial velocity in the y dimension, multiplied by the time interval, plus its initial position. All those things add together to give you where you are later on. Now, this is a quadratic, so we would want to describe, the graphs that we've looked at so far have been very linear, so we would want to know why we have a curve, as a quadratic would be. All right, so let's drop an object in gravity again. What would the position versus time graph look like? We had a position versus x position and y position versus x position, but we didn't have it versus time. So this is what it would look like. We've got a negatively sloping curve here. It's becoming more and more negative through time. Of course, we would also have, this is a parabola, so we would theoretically have a left-hand side also. We'll talk about maybe where that could be. But just for an object that's dropped from a high position to a low position, this is what it would look like. Okay, so through time, what we would find is, notice that here we have from here to here is the change in position. Then from here to here, it's hard to draw, is the next change in position. But as I look at from here to, let's say from here to the next point to here, that's the change in position. So the y displacement is increasing in the negative direction. Okay, our acceleration, and this is in feet, so the acceleration is 32 feet per second, but this 32 feet per second is in a downward direction, and that's where we get actually the true value of the acceleration due to gravity is negative 32 feet per second, and that's related to why we have this negatively sloping curve. If we go back and look at our quadratic on this page, this g is a negative 32. That's going to give us that downward facing or downward opening parabola with that negative curve. All right. So how about horizontal position versus time? Look at the free body. So this is for the same object that's thrown. Well, let's take an object that's thrown off of that 25-meter high cliff, and look at the object as it enters the air. As it enters the air, we have gravity down, but we have nothing else. So there is no force in x dimension. So what sort of pattern would this look like graphically if we're looking at just how the object changes in the x position versus time plotted? Okay. This is what it would look like, which is the same graph that we had earlier. Okay, so why is that? If there's no net force in the x, then linear constant velocity motion. So let's suppose we combine x and y motion together into one. So this is two-dimensional motion of a horizontally launched projectile in gravity. We've got the y position versus the x position. As we look at the x position, as we read the displacement across the x, from here to here, we get a certain displacement. From here to here, we get a certain displacement. From here to here, same displacement, same displacement, same displacement. But as we look we go vertical with this, and we look at from here to here, you can see you've got a very small displacement as we're going between these objects. If we go from here to here, we have a little bit more, and a little bit more, and a little bit more. It's really hard to draw a straight line here. But what we're finding is that as we go in this direction, displacement increases per time interval. That means we're accelerated. But if we go in the x dimension, so if we go here, so looking at it this way, we have a constant displacement per time. So this is constant velocity. Okay? So does that make sense in terms of the force diagram? And it does if you think about that we have a net force down. So if there's a net force down, we're going to have acceleration. It's going to speed up. But if we have no net force in the x, sum of forces in the x equals 0. That equals constant velocity motion. And of course, when we dealt with trusses, we said that constant velocity motion was at rest, but the constant velocity condition does not have to be at rest. It can be moving at 1,000 miles per hour, and it's still constant, then there's no net force. So what happens if a projectile is launched at an angle? Suppose we launch at 90 degrees. That means we fire the projectile straight up. So let's just take some sort of projectile launcher, rocket launcher, pistol, whatever, and we fire straight up, 90 degrees, 100 feet per second. What would it look like? Okay. Well, if you just think about what you know, you probably realize that if the object is fired straight up, it's going to rise. And it's going to begin very quickly as it comes out of the launcher, but it's going to slow down, and it's eventually going to get to a point where it's going to reverse direction. So for it to do that, for it to reach a point where it reverses its direction and falls back down, speeding up as it falls back down, then it has to be accelerated. It has to slow down as it rises and speed back up as it falls back down. So this is what that's going to look like. If we're looking at the change, this is versus time, so this is not really showing your x position. This is showing the y position in gravity launched at 90 degrees. We can see that if we start here at the origin, we're going to rise to a certain location. This is the maximum height in the y that we're going to reach right here, and then it's going to come back down. You'll also notice that as we go from here to here, compared to from here to here as we're reaching the max, there's more displacement here than there is here. And the reason for that is that up here, in this area, it's moving slower than it is down here, because each of these points are marked at equal time intervals. So if we have a half second, I believe that's what I have this going at, we're starting at 0, a half second later, we're almost 50, so probably around 49, then we're a little bit less than double that, then a little bit less than doubling that. So we keep having these displacements that become less and less and less. And then when we get to this point, it begins to, the next half second, it's actually going to drop a little bit. So at this point, it is actually reverse directions. So what happens as the angle lowers to less than 90 degrees? Well, the changes in the y position and their changes in the x position, but they each happen independently of one another. The two dimensions happen as if the other one was not happening. So x does its thing, y does its thing, or the object changes
its location in the X and the Y at different rates. So we can actually go and look at a logger profile here. And what this is showing, this is X velocity for the object that's launched versus time. So you can see that I've got X here versus time, and you can see that the spacing, as we go from left to right, spacing is very consistent. Okay? Meaning that in the X dimension, as time passes, X position is changing in a constant velocity way. Now we can switch. Let's change axes here. Now let's go to y velocity as a function of time. Okay, and what we find is that you get sort of an unusual pattern here, and this is not actually showing everything. We start out at 100 meters per second, or I'm sorry, feet per second. So y velocity is 100 feet per second, and then it's gradually decreasing. So the rate, we have a rate of change here, which is the slope of this this plot. I could put in a straight line here and get that slope, or at least I could try. There we are. And we find that the slope of this is negative 32 feet per second per second. So I'm changing velocity from 100 feet per second to eventually 0. So what's happening here is that, and this is really just looking at one side of it. This is the object when it leaves the launcher on the ground. This is the object when it reaches up here close to 0. I'm not showing the entire graph, but it's reaching the inflection point where it's going to return back to the ground, or reverse directions and come back to the ground. Key is here that if I look at velocity versus time, so let's try this also. Let's look at position in the y-axis versus time. Okay, and you can see here that we've got the y position is, we've got position versus time graph that's a curve. When you graph this as the change in position versus time, it goes to our y position versus time. There we are. We actually want initial, we want y velocity versus time. There we are, right there. And that's what we end up with. We end up with that negatively sloping curve, because if you think about this for just a moment, if you go back to the previous graph, which was y position versus time, what we're graphing when we have position versus time, the slope is the velocity. The slope of this graph is the velocity, and the slope is starting out here as a positive. So we've got a positive velocity, the object's moving up, but it's becoming less and less and less. So our slope begins over here rather steep, but by the time we get up here, we have a less steep portion of the curve, so our slope is less steep, or becoming closer to 0, and then eventually when we get over to this side, we're going to have a negative plot. So how can we use all that information to help us predict the range of a projectile? Well, we don't need all of that necessarily to predict the range of a projectile, but we do need to know that the projectile launched at an angle does different things in different dimensions. It's constant velocity in the x, it's accelerated in the y. So measurement of time, though, especially if you're over a short distance like you throw a ball, measurement of time is often a problem because everything happens so quickly. You only have the time from where it's launched to when it hits the ground. So that could be a very short period of time. If you drop something from the height of your head until it hits the ground. So if you start it when you drop it from the height of top of your head to the ground, to stop it, you barely have time to accurately start and stop a stopwatch. So how can you predict range without knowing the time of flight? And that's really what we're going to look at here in the end of this presentation. And this is the method. First, calculate the initial velocity and assume that it stays constant throughout the test. So if we're going to have some sort of test, or we're going to launch, and we would say that we would have a constant launch velocity. Calculate the resulting range for the specified angles, and then you plot the range versus the angle and use that to predict the angle for the specified range. Okay, so first, calculating the initial velocity, we pick an angle. We shoot the projectile over and over again at a chosen angle and calculate the mean, or the arithmetic average. We then use the angle, the mean range, and gravity to calculate this. By gravity, that's the acceleration due to gravity, to calculate the initial velocity. So finding the formula for initial velocity, remember that range is equal to VI cosine theta, where VI is the velocity of the projectile along its trajectory multiplied by time. And the y position is equal to VI sine theta times t minus 1/2 g t squared. Now, I will tell you that when I wrote this earlier, I went with y equals negative 1/2 g times t squared, where I put the negative here because g has a downward direction, plus VI, and we've got sine delta t, or sine theta, excuse me, delta t, and the reason for this is that VI sine theta equals VIY. So I actually wrote this originally, when I wrote earlier, I wrote this as plus VIY plus YI, and this is times t, VIY times t. Now, this is a final position. Okay, so final position equals 1/2 the acceleration due to gravity times time plus VIYT plus YI. If we move this over and say YF minus YI, this is actually going to be what's showing here, which is technically a delta Y, which is how far the object has displaced, not a position. Y is a position, delta Y is a displacement. So because VIY is equal to VI sine theta, we can substitute that in here. Both of these involve time. Okay, so this gives you the x range, this gives you the y displacement. So this technically is also a delta x, but x is fine. X max. So we can derive a new equation to get rid of time, essentially. We can eliminate that variable. All right, so we've got y equals VI sine theta t minus 1/2 gt squared, or 0 equals VI sine theta t minus 1/2 gt squared. Now, here's a little caveat to this. Project Lead the Way just throws this value in, but this is an important limit to how good this equation is going to be. If we have a projectile that's launched from this position and fires to over here, so it takes a trajectory like so. Yeah, missed my own point. So we end up over here. If we find the displacement in the y, here's our initial position, here's our final position, and we're looking at along a y-axis, so yf minus yi, if these two numbers are the same, that equals 0. So that's what we have here. This is a delta y, and the displacement is 0, which means the projectile ends up at same height it started. Okay? So in other words, if we had something like, if we had a basketball goal over here, and where someone shoots a ball and it goes up like this, if we have this height versus this height, this equation that we're going to have would not work, because the ball at the goal point, which we at the actual hoop that we might be interested in, it's not going to be at the same height from which the player launched it. So this equation would be limited in that way. All right, so we rearrange now. So we've got 0 over here, and we're subtracting, or actually adding, the 1/2 gt squared to the other side. So that's now positive. 1/2 gt squared is equal to vi sine theta times time. And rearranging again, we get vi. So all we're doing is cross multiplying here. Actually, there's some cross multiplication and division as well. Gt squared divided by sine, divided by 2, there's your 1/2, sine theta t. We can cancel one of our t's, and we have vi, actually this is what's left, vi equals g times t. We're eliminating the 1, we're not writing it, it's understood, divided by 2 sine theta. Okay? And we take our definition of x is equal to vi cosine theta t, and we rearrange it for t just by dividing by vi cosine theta. And we would say that t is equal to x over vi cosine theta. So we have a definition of t here. Okay. So we can take this equation, vi equals gt over 2 sine theta, and t is equal to x over vi cosine theta, and we can substitute that in for t. So this all gets placed in for t. And the end result is that vi equals g times x, where x is the range, divided by 2 times vi times sine theta times cosine theta. And we can simplify a little bit further by having the double angle formula, where sine, 2 times the sine theta times cosine theta equals sine of 2 theta. If you're doing pre-calc, you've done trigonometric identities. So we're going to make use of that. This equation right here would actually work as it is. There's nothing wrong with it. This is just going to simplify it a little bit. And we say that vi squared is equal to g times x over sine theta. All right, so if we go back for just a moment, notice that the vi is now squared. That's because this has been cross-multiplied over to here to give vi squared. And then we've got 2 times sine theta cosine theta. And that 2 times sine theta cosine theta is just simplified to the sine of 2 times the angle. So notice that this is the way that you would handle this in a calculator, is that you would take the angle. If the angle is 45 degrees, then you would say 2 times 45 degrees and then take the sine out of it. All right, so our final equation, we've got, if we are solving for just vi, we can say that vi, taking the square root of both sides here, vi is equal to the square root of gx over 2 sine theta, and rearranging the equation so that we're solving for the range. Okay, so we're actually solving for x. Then we're going to have vi squared times the sine of 2 theta over g is equal to the range. This equation is sometimes known as simply the range equation. And it's also important to note that it does require that the object start at a certain height, be fired at an angle or whatever, but it comes back down to the same height. So the range is always going to consider the same height. And using that formula, the range can be calculated for various angles without knowing how long it takes. So this is time independent. And that's the end of the presentation, and hopefully we'll have some time to do some problems in class so that you can practice on some of these concepts with projectiles. The end.